Not change it. Yes. Can we start now?
Good morning to all gathered here.
Sir, good
The
morning, sir.
science, sir,
Yes,
good morning.
sir. Sir, slide is visible now, sir. Can you go to the full screen mode, sir? Yes. Good morning. Yes, sir. It is moving, sir.
Good morning.
Good morning, sir. Anita, ma'am, shall we start now?
It is moving, no?
Yes, sir.
Is it moving?
Yes, sir. Yes, sir. It is moving, sir.
Slides are moving?
Yes, sir. It is moving, sir.
Okay, okay. Okay, thank you, thank you.
Okay, sir.
Sir, shall we start,
The
sir?
science of
I'm ready.
sir, who won the Nobel Prize of Physics. It was on this day in 1928 his discovery of Raman effect came to light at Indian Association out to raise awareness about the importance of scientific applications in our daily lives. The theme of this year 2024 is Indigenous Technologies for Vikshit Bharat. Today, February 28, 2024, we all have gathered here for celebrating this National Science Day with a small seminar with our special renowned personality, Dr. Amitava Mitra, Professor, Department of Physics, Head, Center of R&D, Scientific Instruments, Jodhpur. Dr. Amitava Mitra completed his MSc in Physics at University of Calcutta in 1981 in the field of disordered materials. After carrying out his PhD at Institute of Applied Magnetism with Spanish Government Fellowship, Dr. Mitra sir joined at CSIR, National Metallurgical Laboratory, Jamshedpur, India, in the year 1990 and developed NDE and Magnetic Materials Group. He became chief scientist in the year 2010 and professor of Academy of Scientific and Innovative Research, CSIR NML. He has guided 6 PhDs, 7 MTech students for their thesis. He superannuated from CSIR NML in the year 2019 as a head research planning and business development division, and he won Best Metallurgist Award in the year 2006 by Ministry of Steel, Government of India.
India Institute of Technology, Jodhpur. Before that, I was with CSIR Laboratory, National Metallurgical Laboratory at Jamshedpur. And most of the work, what we carried out, or what we will present here has been performed at the National Metallurgical Laboratory, Jamshedpur. I will talk about this amorphous and nanostructured magnetic materials for transformers, and also point out, if the time permits, whether this can be also utilized, how we can utilize this material as a sensors for structural health monitoring of pipeline. When we are considering a magnetic materials, we can make it the two different categories of magnetic materials. One we call as a hard magnetic material or the permanent magnet, and one is called the soft magnetic materials. The emphasis for the two varieties of these materials are also different. In one case, we want this hysteresis loop, what you are looking here, should be as narrow as possible. And one case we want that should be as fat as possible. So one should be very slim and one should be very fat as possible for the hard or magnet. And this includes, when we are talking about this, there is a parameter called coercivity, which should be as high as possible for the case of a permanent or hard magnet. And for soft magnet, it should be as small as possible for any applications point of view. Now, if we consider the applications point of view um, of short magnetic materials, we will consider here not mostly, only the short magnetic materials. We will not talk about the hard magnetic materials. It is the short magnetic materials which is of importance today. And what is an applications of the short magnetic materials? There are two major applications. One is the transformers, and others is the sensors and transducers. And for the sensors and transducers is also of different applications. It can be used as the target detection and tracking. It can be used as a space research. It can be used as the biomedical applications. And we work at National Metallurgical Laboratory mostly in another area, that is actually characterization of aging steel instead of completely discarded plant and going for a new plant. So this is the very good areas work. But one problem of this area, as the magnetic, we are concentrating on the magnetic properties also. This is only useful for components which are the steel structure. But if you see, most of the heavy structure is made of steel. So that is an advantage. Now, if we consider we'll first concentrate about the transformer materials, and then, if time permits, I will just give an example of the material what was developed at the National Metallurgical Laboratory, how it can be used for pipeline inspections. And as the theme of the entire proceedings is on the indigenous materials, the total work what we will describe, it is the indigenous development of materials. Not only the materials, the applications also are done indigenously. If you consider the short magnetic materials, these are the basic materials: iron nickel alloy, which is sometimes called palm alloy. Another category is iron cobalt alloys, and also the ferrite, manganese zinc ferrite. These all are short magnetic materials, and these are the very conventional materials. And iron nickel alloys, which is called palm alloy, which is just at the bottom. This is a very high permeability and used mostly in the sensor elements. Iron cobalt alloys, it is very high saturation magnetizations and are used for what I call where we require a very high temperature materials, because the cooling temperature is very high. And its commercial name is Parmedur. You see, I have internationally don't talk about the silicon steel. Silicon steel, this is basically iron silicon alloy, which is named as commercially as a silicon steel. And most of the transformers today, which is available or you are seeing in the market, is made of, its core is made of the silicon steel. You see, although we are talking about the steel, but if you see the true behavior of a steel, where we require silicon as low as possible. And there should be, in steel, there should be a small percentage of carbon. But when we are talking about the silicon steel, our requirement is as much as silicon possible and as low as possible the carbon content, because the carbon which is go into the interstitial site, that is very, very detrimental for the magnetic properties of a material. But as the process of making, just like a steel, we make the processing, that is melting, casting, rolling process. This silicon steel is also made in the same fashions. So that is why it is called the silicon steel. And you can see in the graph where we have put a saturation magnetization versus the permeability. Our major goal for development of magnetic materials is how we can go higher and higher the saturation index, saturation magnetization, and I can go for the same material, how much higher and higher we can go for the permeability. So a good soft magnetic material should have a high permeability, at the same time a higher saturation index. Now you see the total market of this electrical, this is also called, this silicon steel is also called the electrical steel, because its a major market or major application is in the transformer, where we are transferring electrical energy from one end to another one. So that is why it is called also silicon steel and also called the electrical steel. And this is showing how this market of this electrical steel in the worldwide, how it is increasing day by day, day by day how much it is increasing. So this is a graph which is showing from 2018 to 2025, and basically it's showing how demanding these materials. And in fact, if we consider the soft magnetic materials, it's major, more than 50% of this material is used for the transformers of this transformer core. In total, soft magnetic materials, if we can understand. So the major market of the soft magnetic material is as a transformer core. Now, if electricity which is generated at the power plant, where there is a rotor which rotates with high speed using a what I call steam, and just by the Faraday's laws of inductions, they have a magnet and there was a coil, and by that the Faraday's laws of inductions, the power generated at the generating stations, and the power which is generated at the generating station, that is now being doing the transmission. You can do the second one is the transmission, and from the transmission it goes to the distribution station, distribution line, that is the substations and so. So high voltage electricity transform. See the total how we have a substation step down transformers, and then what you are saying just on the street a distribution transformers which is directly going to our household supply or even the public use. So the entire system, so we can understand, we require a lot of transformer to transport electrical power from generating station to our use. And if you see this transformation process, if you prepare 100 units of this in the generating station, only 65 units is available for our consumptions. But where this losses is taking place, there are 5% loss, transmission loss, about 5% transmission loss. So when the substation is getting is the 95 unit hooking from this line, there are many body are using this one, so you cannot, government is not getting the right type of revenue from this. But this 15 to 20%, which is the technical loss, that is an opportunity for the material scientist how we can um, uh, reduce that 15 to 20% technical loss. So this loss is basically an opportunity to develop the energy efficient transformer. So if we can develop a better and better materials, how we can reduce this 29% losses. Now, if you see a basic design of the transformers, this is the basic design, and where these rectangular portions, what you are seeing, is basically made of hot magnetic materials. And right side we have um, a primary coils, and the left side we have a secondary coil. So high voltage transformer, which is coming from the generating station or from the substation, going to substation or the household supply, the secondary windings, which is called the secondary windings. And at the secondary windings, we have to put the load. So when the load is connected, you see where the load is connected, there is a current is flowing to the secondary. But when the load is not connected, then there is nothing is coming in the secondary. But at the primary end, there is always a current flowing in the circuits. So we can determine what about the loss is taking place. This loss is a load loss and also the no load loss. This is something when we are going for the charging of our mobile, we have a device, the charger, and I am sure if we use at the houses, we never put it off at the from the main or from the source. We just take it out this mobile after charging. So our switches are on, but there is no load. So as we are talking about our switch is on and there is no load as we have taken out the mobile. So at the secondary windings, no current is flowing, but in the primary winding, the current is continuously flowing. But if I put a switch, if we put off the switch at the put off the switch, then current will not flow in the primary windings too. So we can understand there is a load loss and there is no load loss. In fact, the duration of the no load loss is more compared to the load loss period. So load loss, when you are talking about, the total period is much lower compared to as the at no load loss period. So we have to be very considerate that my materials has to be developed in such a way that uh, it should reduce the no load loss condition, losses during the no load, and also the losses when the load is there. So we can consider the total loss is equal to no load loss, that is the core loss plus load loss. And for this total losses, actually we can consider there are two components. One is called hysteresis loss. The hysteresis loss means you have seen that hysteresis loop, and I will also come to this hysteresis loop, and also the eddy current loss. Why this eddy current loss is there? Because we have sending a current which is at the frequency around 50 hertz. So as the 50 hertz frequency is there, there will be an eddy current generated, and that eddy current loss is taking place also. To reduce the eddy current, we actually the core what you are seeing it, we make it in a lamination form. So lamination form was made to reduce this eddy current loss. But if we have a better material which has a less eddy current loss, So, so total losses will be reduced. So again, eddy current loss has a two component, which is called the classical eddy current loss and the anomalous eddy current loss. Now let us think up quickly about this soft magnetic material or any magnetic materials. It has the domains, and its domains are oriented in such a way. The domains are in the spontaneous magnetization state, and they are oriented in such a way that from the outside, and though no field is applied, there is no um, uh, net moment in these materials. But so if we can exaggerate this domain position, it is something like that. It is not a very sharp line. It has some width, which is called the domain wall width. And this domain wall width is also taking a major role um, for a materials which has to be a soft magnet or a permanent magnet. So if we now apply a magnetic field in this one, you see there are the regions in between the two, the domain two position, where the magnetic moments are oriented and going from one position to the other position, and it is inverting the other end. And when we apply a magnetic field, the domain wall movement is taking place, and you can understand this one movement, how this taking place. So now it is moving towards the right hand side, and is become a one domain structure. So the domain wall moves from one position to the other position, and when it is getting the saturation, the all the moments are oriented in one particular directions. So if we plot this magnetic field versus the induction, so at initial stage, which is called the reversible motion of the domain, then we have the irreversible motion, and then it gives the domain rotation, and we got the saturation. And if we go for the complete cycle, then this area is called the anisotropic energy of the material. And if we go for a complete cycle, we will get a hysteresis loop, and total energies of this hysteresis, or total area under the curve, is called the core loss, or area under the loop is called the core loss. So our attempt should be as low as possible this core loss, and also how can reduce the um, how we reduce the eddy current losses. So as we told, the losses, the hysteresis loss and the eddy current loss. Now, if we consider the silicon steel, if we go on increasing the silicon steel, you can see the total loss, which is coming, it is reducing as we increase the silicon, and it becomes minimum. This loss is minimum when it is about 6.5%. And then if we go on the resistivity measurement, if we see again the resistivity measurements, because why the resistivity is important? Because resistivity is important. If the material has a high resistance, then the eddy current loss will be less. Eddy current loss will be less because the eddy current, that the loss here also, this is I square R. So if the resistance is high, then I will also be less. So we have a less because I is varying with the square of its magnitude. So if I is less, then the eddy current loss is also less. So, but again, you can see it is linearly increases up to around 6 to 6.5, and after that it is deviated from its linearity. And you see how you process this material. So you can understand now the 6.5% silicon steel is a better materials because its losses is less, and also the resistance is high. When we process this material, as I told that this processing of this material is the same way we prepare in the same way we prepare the steel. That is, it has to be melting, it has to be casting, and then it has to be a rolling process. Rolling is there are two big rollers, just like you have seen that sugarcane juice is prepared when this sugar cane is pushed in the tube roller. Here also the steel in its hot condition, it is passed through the tube rollers and it reduces this thickness. So one by one passes, we reduce the thickness. But you can understand this is possible if this material is not brittle. Let us see how we can, in the case of with the silicon content, how it changes. You see here we have plotted uh, reduction in area and percentage of silicon, how we can reduce the silicon, and how we can proceed to the further. So if we see this one, this is this a very good formability is possible when we are um, around 2.5% of the silicon, and then it decreases drastically. It decreases drastically, and the um, formability decreases drastically. And if we go on increasing the silicon, and we will find that after 5, it is very, very difficult to go for, because the material is uh, uh, very, very brittle. So this area particularly can't be cannot be rolled when silicon is greater than 5%. So we have a small window, although my 6.5% gives a better magnetic properties, but we cannot do it because of this, uh, um, because of the formability problem. We cannot form, we can make not reduce this, we cannot make it in the thin sheet. And if we cannot make it the thin sheet, I cannot put in the laminated form. And if we cannot put in the laminated form, eddy current will be very high. And other properties is also, handling is also very, very difficult. So we have a very small window to go for these materials. Now, is another things are what is observed actually, that the grain size. If we put the grain size and the coercivity of this material, if we see for the higher and higher grain size, your coercivity will be as low as possible. And there is a region which is called ds diameter, where it is actually single domain size, and where in the single domain size our coercivity is high as possible. So one condition uh, for the hard magnetic materials, if we can go for the domain size compared to the grain size, comparable to the grain size, then the material HC will be high. That is the criteria for a hard magnets. So we have now a large domain size, a large grain, low coercivity, and low losses. And if we see this one, the silicon steel, now there is now if we go for around 3.5% of silicon steel, we can get a grain size is quite high. And this is called a silicon steel, which is called cold rolled non-grain oriented silicon steel. So now we come to the silicon steel, which is 3.5% silicon, not 6.5% silicon. And we have now a variety of the silicon steel, which is called cold rolled, non-grain oriented silicon steel, and another varieties of silicon steel, which is called cold roll. And you can see the grains are oriented along one direction. So we have now two types of silicon steel: cold roll, non-grain oriented, and cold roll, grain oriented. Um, in fact, still in India, cold rolled grain oriented silicon steel, commercially we are not producing. Some effort is going on, um, Jindal Steel, to procure to prepare this CRGO, which is called as CRGO. But the CRNGO is produced many of the steel industries. Out of this um, uh, CRGO, which is the better varieties, again, there are two types of silicon steel. One is called regular grain oriented, where the orientation and the easy axis has 7-degree misorientation, and another is high grain oriented steel, HGO, where 3% misorientation from the rolling directions is taking place. So I am not able to orient all the field along the rolling direction or along the directions of the easy axis. So if we consider now the losses, what is taking place for the regular grain oriented and high grain oriented, you can understand regular grain oriented, this losses is about 0.6 watts per kg, and then on HGO it is coming down close to 5.5 watts per kg. And you can see what are the various varieties of the materials, what are various varieties or various losses: hysteresis loss, classical eddy current loss, and excess eddy current loss. Now, if we again see this material, if we consider the magnetic anisotropy, as these are basically a crystalline, polycrystalline material, we have a major anisotropy is coming from magnetocrystalline origin because of the crystal orientations. And we have another one which is called magnetoelastic anisotropy, which is coming because of the magnetostriction constant of the material, and another is anisotropy. You see, now if we consider the major anisotropy which is coming from the magnetocrystalline anisotropy, and if we now give our effort, if we can eliminate the magnetocrystalline anisotropy, then I can reduce the anisotropy energy of the material drastically. And as the anisotropy material drastically, I can reduce the hysteresis loss also drastically. So our effort will be now how we can reduce this one. Magnetocrystalline anisotropy, while because of the crystal structures. Now, how the crystal structure is coming? If we now go for this melting of a material, and now during melting of the material, I am giving a sufficient time during cooling so that an equilibrium structure comes, and crystalline structure is a very equilibrium structure, and we got a crystalline structures. But instead of giving the sufficient time, if we quench the material from the liquid state to another solid state, but retaining the liquid structures as it is, so if we go like that, then I can eliminate the magnetocrystalline anisotropy of that material. So this is the basically the philosophy of going for the amorphous material. Why we are going for this amorphous material or amorphous steel or metallic glass, whatever you call it, because this is a glassy structure. It does have any crystalline anisotropy. So how we can do it? We can do it by rapid solidification. What is the process of the rapid solidification? You have a copper wheel, and you can go with this copper wheel. You can rotate this copper wheel, and the liquid metal is poured on this copper wheel, and we can go as a form of strip, very thin strip, around 30 micron thickness, and we can get a um, uh, in the form of thin ribbon, we can get this material. So this is the materials which has the capacity to produce 1 kilogram of materials, which was developed at the National Metallurgical Laboratory for development of these things. Let us see whether I can show you a video, some video where you can understand what is the process is taking place. Just see whether I can get it because uh, there is a problem. Let us see whether I can show you how to go. Just give me a time. Share. Share screen. Enter screen. Are you able to see that video? No. Are you able to see it?
Yes, sir. Yes, sir.
Yes. You see, this liquid metal is now pouring on that wheel, and we are getting continuous ribbon. So I'm just doing once more. So you can have that ribbons in that form. Iron, silicon, boron, these are the type of materials. Now, if we consider this material and compare it with the hysteresis law of the silicon steel, you can easily see that amorphous iron, boron, and silicon has a very narrow loop as compared to the grain-oriented silicon steel. So, and there is a huge reduction in the loss in the hysteresis loss, huge reduction in the hysteresis loss, and at the same time, uh, because of the amorphous structure, the resistivity of this material is quite high as compared to the crystalline structures. And if we now compare with this material to the regular grain-oriented and highly grain-oriented, and we have the amorphous alloy or the metallic glass, whatever you see, the things which for the highly grain oriented, which is coming around 0.55 watts per kg, uh, is reduced to less than zero point 0.2 watts per kg. I can understand what is the how much is reductions in the hysteresis loss, how much is reductions in the eddy current loss, both excess and the classical eddy current loss. And this material was first developed in 1973, and after that, at the USA, because it come down to almost 34, 35 degrees Celsius. So there is a lot of advantage of using these materials. And there is a large number of alloys which was developed at the National Metallurgical Laboratory. And you see, these are the various transformers. And basically, if we can say, there are industries already has developed in India who are producing this material commercially. In fact, just at Haryana, there was a company which is coming up, Advanced Materials. Uh, mm, um, its name is probably Advanced Magnetic Materials. They are developing their industry in consultation with the National Metallurgical Laboratories. But these are the example which was initiated at the USA, and these are the world biggest 12 megavolt ampere oil filled amorphous metal transformers, which was used in the Korea. And but you see, all the aspects you cannot get in one material. So it has a disadvantage also. The major disadvantage, because lots of boron and silicon is present here, its saturation induction is really much less as compared to the 3.5% silicon steel. And that is why, for the applications where you require the magnetic induction level very high, this material is not very good. So otherwise, you can see how much is the reductions in the core loss. But as soon as it is going beyond 1.5, 1.5 probably is a useful magnetic induction level for this type of material. So we can understand it will be very difficult if we want to go beyond 1.4, and so this material is not advisable. Now, if we can see the applications of these materials, as we told, as a transformer materials, you see soft magnetic materials market share actually for the transformers, it is 55.9%. And next is the shielding material. Next is the shielding materials, and rest are all are different types of sensors and development. And this is the Asia specific soft magnetic materials market size. So it is ever increasing market sizes. If you see worldwide where it is produced, this is produced mainly at the USA, Japan, China, Korea, and nowadays India has also started producing these materials. And there is, if you go one more step, actually, if you see, there are enough space is also available for this development of newer materials, and then we are considering a nanostructured materials. And this is the, you see, this is the materials with the ascast, and after that, if we go for proper heat treatment, we get a materials which is called the nanostructured magnetic materials, and this can be produced in a large quantity. Means the same system, what you are producing in a large quantity, this amorphous alloy. Now you add niobium and chromium in it. Actually, niobium is added so that the grain size cannot increase, and copper is added as a nucleation site, and then we can have an amorphous matrix nanoparticles are dispersed in the amorphous particles, and this led to a coercivity much higher, much lower than this what is we got in the amorphous system. And here you can see the coercivity reduced with the d to the power 6. So here what is happened, basically within one domain you can have large number of nanoparticles. Within one domain wall width you have large number of nanoparticles, and by application of small field you can see the domains are rotate along the magnetic field. So this process is taking place in so small field that coercivity is become as very low, and this is also used for development of different small transformers, or the um, small transformers, or its application is in the sensors, different type of sensors, because its coercivity is extremely low. Coercivity extremely low indicates that its permeability is extremely high. How much time I have having? Hello? Do you have another 5 minutes, 5 to 10 minutes? Hello? Can I take another 5 10 minutes? Or I will stop it?
Yes, sir. Please, sir. Yes, sir. Yes, sir. Yes.
Okay. So I will just say, I told about how this material is used for a transformer as a transformer course, and what is an advantage of its transformer course. I will just explain it, as I told at the beginning, how this material can be used for the structural health monitoring. Particularly, I will give an example for a pipeline inspection. I will quickly go. You see, we have a large number of pipeline. Is a huge pipeline is going from one place to another. You may not realize, but the oil transportations from one state to another, one depot to another, there are pipeline laid uh, throughout India. Not only throughout India, it is very all the inter uh, inter-country delta L by L change in length by the total length by the application of magnetic field. So what is happening if we consider this one? What is happening? It is a tube. If we now apply a wave at one end, then the wave will propagate along the thickness, which is called the guided wave. Suppose, I don't know whether you can see it. I cannot see it. So what is happening? The wave, if we can make a wave here at one end, and this wave at one end, and this wave will move. This wave will move throughout this pipe and come back from the end, and again this excursion is taking place. This is what I call a coil. We have a coil, transmission coil, receiving coil, and also a coil which is we call it the we produce a DC magnetic field also. So this is the exact setup, and this is also a equipment which was developed at the National Metallurgical Laboratory. And you see, this is a type of signal which we call first back wall, second back wall, third back wall, and so on. Now, if we have a cut here, oh, if we have a cut here, then you can find that in between the two signal, we have a signal. This is a cut, and this is we have simulated the corrosion. So we have the signal here. One is the cut, and one is the corrosion. So if we now know what is the what is the velocity of the wave which is propagating along the tube, and then from knowing the velocity and where the time we are getting this signal, I can understand it which location. See, this shows how much the signal is there. This is that even if the line is underground, we can also measure the signals. And if there is a hole, we also can make the signal. So these are the application. I am not going to any details of this other activity. So there is a lot of persons involved in this work, and I had a lot of students from NIT Trichy who did the MTech with me when I was at National Meteorological Laboratory, and we have the scientists and the PhD students. And this device is now commercially available in the market for use in the petrochemical industries. And thank you once again for the authority to giving me the opportunity to express, to share my knowledge to among the participants for this proceedings. Thank you very much. These are some of the pictures of the Rajasthan. These are the fort we are having, and at the left hand side we have this IIT clock towers. Thank you very much.
Thank you, sir.
I'm ready to any questions is there. I'm ready to give answer.
Yes, sir. In the chat box itself, there is a no question, sir. But everyone is saying that it is everyone nice, interesting presentation, very nice session, like that. They're commented, sir. So
Chat
participants,
box,
if
I
you have
think there
any
is no
queries,
comments
please.
in the chat box, no? Thank you very much and wonderful and productive. Okay.
Sir, there is one question from Venkatesh.
Yes.
Yes, sir.
Can I
Being
just
an
ask
amorphous,
the question?
yes, sir.
Please go ahead.
It is amorphous material. What is the lifetime of the sensor?
You see, if you use at the ambient temperature, this will go at least 20 years of its time. Only at the room temperature. The testing was carried out. Okay, thank you. Thank you.
Yes, sir. Thank you,
I
sir.
thank
Another
the
one?
and its applications. It was very interesting, sir. Thank you, sir. And its applications. It was very interesting, sir. Thank you, sir. I thank one and all for all who are part of this National Science Day seminar. Thank you all.
Thank you. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir. Dear participants, we have to start the second session today. Yes. Another one, please. So, dear participants, today is the third day of FDP. Anita ma'am.
Yes, sir. Will proceed, sir.
Yes, sir. Please, sir.
Good morning, Dr. Shakti.
Sir, good morning, sir. Sir,
Now
the
sharing.
program. Yes, sir. Sir, the small minute,
No.
2 minutes, sir. The person will give the small intro about you, sir. Then we can
Yeah,
start.
but I have to share the screen, no?
Yes, sir. You can share the screen, sir.
But it's not
You can share the screen in a full screen mode, sir. Then only it will
full
be easy
screen.
to. Yes, sir.
Okay,
Entire
okay.
screen option.
Yeah.
Shall I start?
Yes, ma'am.
Shakti, sir.
Yes, madam.
Good
Please,
morning,
ma'am.
professors. Okay, sir. Good morning, professors. It's my pleasure to welcome you all for the second International FDP on Advanced Functional Materials, Energy, Environment, and Sustainable Rebirth has obtained both MSc and PhD degrees from Mangalore University. After working for 6 years as lecturer in Vivekananda College, Puttur, he moved to NIT Karnataka in the year 1998. Presently, he is working as professor in the Department of Chemistry, NIT Karnataka. He was a visiting scientist at Korea Institute of Energy Research, Republic of South Korea during 2003 to 2005. He was a Commonwealth Academic Fellow in 2015 at Northumbria University, Newcastle upon Tyne, UK. Professor Butt is a visiting professor in Smart Centre, University of New South Wales, Sydney, Australia. Professor Butt's research interests are carbon nanostructures and its composites for hydrogen storage materials, catalysts, supercapacitors, biosensors, coordination compound, and organometallic compounds. Professor Butzer has published more than 135 scientific articles in reputed international journals. He has about 130 conference presentations too. He has one patent and 3 was published. He has guided 16 PhD scholars at IIT Mumbai, IIT Madras, and NIT Trichy, and other Indian universities. Professor Bhatt is a reviewer for many international journals in the field of catalysis and nanomaterials for energy storage and sensing devices. He has obtained research grant from DRDO, DST, SERB, MHRD, TechTube. Professor Bhatt is having ongoing international projects under Asian India Science and Technology collaboration of DST with University of Brunei Darussalam and Laguna University, Philippines. Professor Butzer has awards to his credit. Brainpool Fellowship from Republic of South Korea in the year 2003 to 2005. Commonwealth Academic Fellowship from UK in the year 2015. Nandibevur Award 2019 from Indian Council of Chemists. He has visited many countries: USA, UK, South Korea, Japan, Australia, France, Germany, Singapore. Now I welcome and hand over the session to Professor Bhatt, sir. Welcome, sir.
Thank you, madam, for nice words, and I hope I am audible to all of you.
Yes, sir.
How about the screen? Can you see the PPT?
Yes, sir. Yes, sir. Yes, sir. It is visible.
Is it in full mode?
Sir, we are visible the screen, sir, but it is not in a full screen mode, sir.
Full screen mode.
Full screen mode.
It is not moving, sir.
Moving in the
Presentation
sense
view, sir.
now is it?
No, sir, it is not moving, sir. So you can stop sharing and you can.
Now I stopped sharing and I will share again. Now
Share. There is another option for full screen sharing, something like that, sir. If you go for a sharing,
entire screen.
Entire.
That is entire screen.
share screen. In the share screen, entire screen is there, yes, sir.
Entire
You click this,
screen.
then you
But,
can go.
1 minute. We just see.
So then you have to click in the middle, then you can share, sir. Now you can go to
Now?
the full screen. Then you can move, sir.
Now is it fine?
Sir.
It is fine, sir. Just move, sir. We can. Yes, Yes, sir. It is moving, sir.
Now,
Thank you,
is
sir.
it all right?
Yes, sir.
Okay, sir.
Yes, sir.
Nice, sir.
Okay.
Thank you, sir.
Thank you very much, Dr. Shakti, and a warm greetings to all of you on the day of National Science Day. And morning you had a exclusive talk about this also. And today I'll be talking on my research experience for the last 15 years. Uh, okay, and during the talk, I'll be introducing my institute photographically, as well as the nearby famous places, food, and all, so that you will be having a knowledge about this place also. This I'm from National Institute of Technology, Karnataka, Surathkal. It's one of the prestigious we have to attend this talk. And in this case, what happens is probably you'll be busy with such your devices, mobiles or laptops, with the searching for some many other events, and finally you may end up with this. We'll try how best we can make you awake, and this is our main building in the National Institute of Technology. Is 40-degree inside this missile. This is a intercontinental ballistic missile, which is we realized that the word poor man vehicle that is not clicked properly, but otherwise, though it is a nano car, it is highly spacious and convenient. And you know that now, what do you mean by nanoparticle? So, nanoparticle, see, this is a basic question is anyone ask, and this will be the response. In general, we say that the particle with size in any one spatial direction within 1 to 100 nanometer. But the definition, the perfect definition will be a different, that says particles with size in any one spatial direction within 1 to 100 nanometer, and their property being markedly different from that of bulk. So this is highly important, because when the size decreases, the property changes, and that is called the nanoparticles. Now, you can see that all of you are physicists probably, and you know that the famous tagline, there's a plenty of room at the bottom. It's in 1859, he said, the Richard P. Feynman said, there's a plenty of room at the bottom. That means you can go down in the size of the material, and definitely you will have a lot of physics or chemistry or biology to explore, or a science to explore. You can see that in this slide, where the naturally available materials which falls in a different size, the atoms below 0.1 nanometer, then you have a DNA, then you have a proteins, antibodies, then carbon nanotubes, then you see there are different types based on their dimension. That's a two-dimensional carbon nanostructure. It's example is a graphene, and you have one-dimensional carbon nanostructure. That's the carbon nanotubes, single wall carbon nanotube, multi-wall carbon nanotubes, and graphene nano ribbons. And then coming to the zero-dimension carbon nanostructures, that's fullerenes, carbon dots, all these are having the zero-dimension carbon nanostructures. Then another material is a graphene quantum dot. It also comes in zero-dimension carbon nanostructure. So the conference of nanotechnology, and the organizer has called the expert in nanotechnology, and he has been introducing into these conferences or audience, and says that the two one-dimensional carbon nanostructure, that is a carbon nanotubes and a nano fibers. So this the carbon nanotube, that's a CNT, is described as a seamless cylinder made by rolling one or several layers of graphite sheets into a tubular structure. So this graphite sheet rolls up to give carbon nanotubes. And we have a different type of carbon nanotubes, a single wall carbon nanotube and multi-wall carbon nanotube. And coming to the nanofibers, so the nanofibers are also the other type of arrangement of graphite sheet, or same graphite sheet, but in a different institute festival is there. And the beach volleyball also be paid. Then the nanotechnology is manipulates matter for a particular application and includes side the professor asked the newly joined research scholars to prepare the nano material to the synthesis of carbon nanostructures. Say there are three different major methods: the arc discharge method, laser ablation method, chemical vapor deposition method. And out of this, the bulk scale synthesis is done using the chemical vapor deposition method, and this is more advantageous because you can have a bulk scale preparation, and it's so versatile, and economically this is the best method because it costs very less. But the disadvantage with the chemical vapor deposition, the CVD method, is that the CVD method is that the man, and this Iron Man, normally we say that if you are very hard, very sturdy, then we say it's a like Iron Man. But when compared to this, what is the property of the carbon nano materials? So carbon nanomaterial is the strongest of ever known material. And if you see this Young's modulus of carbon nanotube is 1250 gigapascal, compared to a high strength steel, it's just 200 gigapascal. And then tensile strength, it is 11 to 63 gigapascal, compared to the steel, it's a 2 gigapascal. Then the density, if you see, when you compare with the aluminum, density is half of that, and that's why it is a highly light material. And most of the time you can see that this carbon nanotubes finds application in lightweight vehicles, lightweight materials, and the lightweight rackets. The tennis racket or the shuttlecock rackets are made by this material because it's a highly light, as well as at the same time it's too strong. And it exhibits the electrical conductivity as high as copper, and the thermal conductivity as high as the diamond. And moreover, the highly interesting part of the material is that it is highly flexible one. Now, until in late 1990, the output of the publication in nanofield was from East Asia, Europe, and USA were similar. But East Asia is now in a clear lead, with the US in a second place. You know that the first man to report this carbon nanotube is Sumio Ichima from NEC Corporation, Japan. And he has reported the synthesis of carbon nanotube in Nature in 1991. That's a multi-wall carbon nanotube. And you can see that in this slide where the professor is teaching the course nanotechnology, and the professor name is Dr. I.M. Chota. And you can see that he is asking the students to write the assignment on this. And by hearing the assignment topic, the student has realized his grade F. So he says, the professor says, my assignments exams will be like carbon nanotubes. They will be small, but 100 times harder than any known material. Now, coming to the history of the carbon nanotube, as I said, in Sumio Ishima is reported the carbon nanotube. This is a multi-wall carbon nanotube in 1991, and in 1993, again he reported the carbon nanotube synthesized through arc discharge method, and in this case, it's a single-wall carbon nanotube. And coming to this, the Bhutanese report in 1993, that's again a arc discharge method. So you can see the STEM images of a single wall carbon nanotube. And in 1993, the chemical vapor deposition method is reported by Jose H. and in or a laser ablation methods. So you can see that this simple the method or the setup, instrumental setup required for the synthesis of carbon nanotubes, where this is a two furnace system. Sometimes one furnace is also used, and this is the two cylinders which gives, one is the argon cylinder, another one is the acetylene cylinder or the hydrocarbon cylinder to supply the precursor. And you have a quartz board here, and it is kept in the quartz tube. So this you can see that this is a preheater is placed on the boat, and the nanomaterials are formed, and thus formed nanomaterial moves to the another furnace, that is E is a reaction of the quartz tube. So this is the exactly the carbon nanotube grows here. So in this case, what happens is we use the hydrocarbons, and this hydrocarbon vapor, when comes in contact with the hot metal nanoparticle, first it decomposes into carbon and hydrogen species. See, hydrogen flies away, and carbon gets dissolved into the metal. After reaching the carbon solubility limit in the metal at that temperature, as dissolved carbon precipitates out and crystallizes in the form of a cylindrical, you can see here, this is a cylinder. So it's a cylindrical network having no dangling bond, and hence energetically it is very stable. So this hydrocarbon decomposition that releases some heat to the metal's exposed zone, while the carbon crystallization that absorbs some heat from the metal's precipitation zone. So this precise thermal gradient inside the metal particle keeps the process on. Now we have two different mechanisms proposed here. One is the root growth method. So in the root growth method, what happens is the catalyst substrate. So you can see here, this is a nanometal particle placed on a substrate across the metal bottom. And here, across the metal bottom. And here, now the CNT precipitation fails to push. You can see here, this is the CNT. Hello? Hello, any problem?
For the disturbance, sir, please continue, sir, please.
Okay. See, what happens is this CNT precipitation fails to push the metal particle up, and thus the precipitation is compelled to emerge out from the, see, you can see here, this is emerging out like this. So it emerges out from the metal's apex, and the first carbon crystallizes out as a hemispherical dew, which then extends up to the form of a seamless graphitic cylinder. Subsequently, hydrocarbon decomposition takes place on the lower peripheral surface of the metal. And as dissolved this carbon diffuses upward, thus the CNT grows with the catalyst particle rooted on its base. Hence, it is known as a base growth model. Now you have another method that is a tip growth method or a mechanism. So in the tip growth method, as I said, the hydrocarbon, it is dissolves in the nanoparticle, and since the interaction between the metal nanoparticle and the substrate is weak, the precipitated hydrocarbon, the carbon that takes away the nanomaterial here, nanoparticle, and thus you can have the metal nanoparticle on the one side of this nanotube, and that's why it is called tip growth method. So depending upon the size of the nanomaterial or the nanometal, you have the different material available. If the size is 1 to 5 nanometer, then it's a single wall nanotube, and the size is 20 to 50 nanometer, it will be a multi-walled nanotubes, and the size is more than 50 nanometer, then you get a nano onion. So this is the model which shows that tip growth as well as the root growth methods. So you can see here in this material what we prepared, a catalyst particle at the tip of the grown nano tube. That's a carbon nanotube. This is a TEM image will support this growth mechanism. Now synthesizing the carbon nanotube using a different catalyst. So we have discovered a few metal formates for the synthesis of the carbon nanotube on calcium carbonate as a support. So this metal formates like nickel and cobalt formate, and cobalt and iron formate, and nickel and iron formate. So the morphology of this pure, so no impurity is observed in XRD pattern. You can see the TGA analysis of this thus prepared the CNT. The purity is better than the 99%. And the yield also, it's really very high. You can see that the nickel molybdenum formate, the combination bimetallic, that gave around 9,100 weight percent, and that's a very good yield. Now this bimetallic and the molybdenum combination yielded very high carbon nanotube. Now we can analyze this. It is explained in these two mechanisms. So here it says that the number of nanotube is determined by efficiency of nucleation stage. Now this nucleation stage is the first stage where the number of nanotubes are formed. And this is the nucleation stage is favored by the cobalt in a higher rate compared to platinum. Platinum is greater than nickel, nickel greater than copper. So cobalt takes the upper hand in this case. And then the length of nanotube is determined by the effectiveness of the catalytic growth with the defect-free or a defect repair stage. So this length of the nanotube, it is without a combination of a cobalt and nickel is chosen, so that we get a better or a defect-free. The formates are metal acetates are taken, and we have changed the sodium chloride as a support from the calcium chloride. So this is the some images of the material what we have synthesized. It is a carbon nano fibers, and the TEM image clearly shows that there is no hollow core in the material. That shows that it is a CNF. And this is a Raman with the nickel cobalt formate, cobalt formate, and cobalt and iron formate, and iron and nickel formate, where the ID by IG ratio just below the 1, and you can see that the materials are they well prepared here, and the CNFs are formed, and the combination give a very good result here. The purity is also more than 98%. Now the catalyst what we have taken. The advantage of this catalyst is that there's a metal formats, either acetate or oxalates. Now, the advantage here is directly it gives nanoparticle. You can see the reactions here, nickel oxalate or a nickel cobalt or a iron oxalate, where on heating, the nickel or iron or cobalt nanoparticles are obtained, and other gaseous species what is obtained that will easily escapes out. No impurities will be remaining. So this this can be achieved in a lower temperature also. That's why we have taken the metal formates, and this is the night view of our institute. And see why this CNT is obtained when we have taken calcium carbonate as a support, and why the CNF is obtained on sodium chloride as a support. Now, the reaction, the reason is very simple. It is nothing but the interaction between the metal nanoparticle and the substrate. So in the case of metal nanoparticle with the calcium carbonate, this interaction is very strong, and that's the reason why the carbon nanotubes are precipitating out, and the carbon is precipitating out as a tube, because there is a strong interaction between this metal nanoparticle and the substrate calcium carbonate. Now, coming to the sodium chloride and the metal nanoparticle, this interaction is very weak, and the carbon precipitate can take away this metal, and it forms the fibers. So this is a growth model for the CNT as well as the CNF on the calcium carbonate and the sodium chloride substrate. Now, you can see in this slide where the beautiful the hand, it is decorated. So decoration also matters a lot for the aesthetic look. Now, what we are interested is we want to decorate the nano material what we have prepared, either the CNT or the CNF. So we have reported a method known as a solvent-less method to decorate one-dimensional carbon nanostructures by metal or metal oxide nanoparticle. So without using any solvent, and this is reported for the first time. So CNT and the CNF, it is anyone is taken and it is treated with the metal carboxylate. It's the dry mixture, and mix it well, and the CNT or a CNF metal carboxylate homogeneous mixture is formed, and then take this heat to 400 degree under air atmosphere. Then CNT or CNF will get decorated by the metal nano oxides. Sorry, the nano metal oxides. You can see the slide here, CNF or a CNT. So on mixing and heating around 400 degrees Celsius, on pyrolysis, the under air atmosphere, the metal oxide is decorated on the CNT or CNF. But on the other hand, if you heat around at 400 degrees Celsius under argon atmosphere or inert atmosphere, you can see that only the metal particles or metal nanoparticles are getting decorated. So you can see some of the some images where it shows that the nickel and the nickel oxide is decorated on CNT. The SEM image as well as the TEM image. TEM image clearly shows that there is in this case it is see the first one, it is a nickel metal nanoparticle, and this one is a nickel metal oxide. Nickel oxide it is. So nickel oxide decoration is seen. And we have prepared even the palladium as well as the palladium oxide decoration on the CNT. Then this is the drone view of our campus, where the academic building and one part of the hostel can be seen. Now, this is a palladium and palladium oxide decoration on CNF. You can see the TEM images where the palladium metal is decorated on carbon nanofibers, and the palladium oxide is decorated on carbon nanofibers. Now, coming to the the zero-dimensional material, that is the graphene quantum dots. Now, the graphene quantum dots can be prepared from many materials like the graphite, or from the chemicals, or the graphene, the fullerenes, then carbon nanotubes. All these can be used to prepare the graphene quantum dots. The synthesis method, as you know, it's a top-down method. The hydrothermal and solothermal cutting, and then electrochemical route. Then nanolithography is another method, and nanotomy is exfoliation, and then ultrasonic shearing is another method, and oxidative cutting is another approach for the quantum dot synthesis. And then coming to the bottom-up method, it's a self-assembly, where you can see that taking the HBC, you can get the graphene quantum dots. And organic synthesis, synthetic approach is also one of the method to synthesize the graphene quantum dots. And the sideway, that is a cage opening of fullerene. Fullerene, when you open it, you get pieces, and that pieces is nothing but you will have a one sheet like material, and pieces of this sheet, that is nothing but the quantum dots, graphene quantum dots. And coming to the synthesis of graphene quantum dots here through the hydrothermal method. So taking graphite, and then potassium permanganate, then sulfuric acid and phosphoric acid. So it's a improved the Hammers method for the synthesis of the graphene, and then the solothermal cutting is possible. They have graphene oxide with the basic pH. It is cut into smaller pieces. Graphene form, it is cut into smaller pieces, and this is nothing but the graphene quantum dots. So this graphene quantum dots can also be obtained by the ion beam irradiation. You get a graphene oxide here, and graphene oxide on ion beam irradiation, you can cut into smaller pieces, and thus the ion beam irradiated, the graphene quantum dots are obtained, and this we have reported in the radiation effects and defects in solids. And this is the place, the beach near our institute, where the kite festival was celebrated. Then you know that the nanotechnology matters because familiar material begin to develop odd property when they are of a nano size. As you know, as the size goes to a nano level, even the yellow gold behaves like a red material. So likewise here, they tear a piece of aluminum into tiny strips, and it will still behave like aluminum. Of the labels, and is a Bosch nanomaterial and its uses. This slide, it looks like little hypothetical. The event normally happens in my place. Those who have watched the movie Kantara, where this is slide where there are a number of applications are listed. The major one is the textile, biomedical, healthcare, food, agriculture, then industrial, electronics, environment, renewable energy, the spaceships, or the aircrafts, and then automobile bodies are made through this material. And coming to the finer material, where the devices, energy energy storage batteries, and it is used as a material for biosensor, then scanning probe tips, and then transistors and all. Now, you can see that the nano batteries is for the future. So the size, we also, you can imagine how the size of the mobile when it was introduced, and now how the mobile size has decreased. Of course, the size increased because we wanted to have a bigger screen here. So this size of the mobile were the increases because of the demand from the bigger screen. Otherwise, you can see that the nano devices, and when you have a nano device, quite normal that you have to have a energy source, and it should be in the nano size. So in this slide, what you can see is the professor who is working on nanomaterial is going for a ride along with his student. And the mobile was, his wife called him, but the mobile was not working, and she knew that the research scholar will be along with the professor, and she called his mobile, and then he gave it to the professor. Then he says, the professor said, "What, my wife is calling and angry that I am not responding? Tell her that I am using the battery of my mobile for driving the car." Now, days are not far that the size of the battery will become in a nano size also. So now, with this materials, we will go for some of the applications, and the application, again, it depends upon how exactly the material behaves with the stimuli. So if the stimuli is an electron, then you can see that the output is an electrochemical one. And if the stimuli is a photon, then you can see that it's a photocurrent is formed. And this photocurrent, now if the electron comes back and gives out the absorbed energy, and that is in the form of a fluorescence. So the carbon material is an exciting class of material and warrant more insight to the understand about their properties. They have shown promising potential for various sensing applications. High surface area and the conductivity of this material is the very good, makes it a very good candidate for electrochemical sensors. And the mechanism for sensing using the graphene quantum dots are customizable, and which offer detection for wide range of analytes. And photovoltaic is a very promising area for the E1D carbon nano materials. This is a two-dimensional material. And then the thin film solar cells are greatly explored for having relatively economical construction and transparent appearance. Then you have two major hybrid thin film solar cells. One is the dye-sensitized solar cells, another one is a quantum dot solar cells. So this quantum dot offers a better color purity as compared to the dye, and better band gap tuning property. So this DICE as a quantum dot solar cell finds an application, or it will open a Pandora box when you do research on this. So this is another drone view of our institute and the campus. Now, we have used this material for the biosensors, and you know that glucose is the one material which is required for us, and at the same time we need to monitor the level of the glucose. Why glucose is required? To have energy. So this energy for the body or the cell is given by this the glucose, but at the same time you need to monitor the level of the glucose, and as the concentration increases in the body, then you will come across the diseases like neuropathy, heart diseases, blindness, skin infection, problems in the joints. Then you have the diabetic food like that, severe dehydration, and you may reach the coma state also. So we thought of using this material for biosensing the glucose, and we have taken the nickel oxide and multi-wall carbon nanotube material for a non-enzymatic glucose sensor. In market, what we get is the enzymatic glucose sensor, but it has got its own the disadvantages, limitations, and that's why we have gone for non-enzymatic glucose sensors. And you can see that it's a plant root and plant root nodule like. So if you see the material here, the SEM images, it shows it is just similar to that. That's why we have picked that name for the title. It's a plant root nodule. So at the 0.5 micromoles, and then the linear range is around 14 millimoles, and the working potential of 5 volt. And you can see here the selectivity graph, where the glucose is tested along with the other possible materials normally along with the blood, and this finds a very it gives a very good response only for glucose, and it's a highly sensitive. And glucose concentration is also where you can see that the R square is an point that's 0.99, that shows that this is a very highly linear one, and it's a better material, and it is published in RSA Advances and Sensor and Activators. So these are the some images of the material, that is nickel oxides, nickel oxide and multi-wall carbon nanotube, and we have added the graphene oxide also to this, and this is the material which is used for again glucose sensors, and the sensitivity is a very good sensitivity of 4244, then a linear range of 19 millimole, and LOD of 0.92, and applied potential of 0.55 volt. Then we have taken the quantum dots for a spectrophotometric estimation of the glucose. So quantum dots is taken, and you can see that how the quantum dots helps here in finding out or sensing the glucose. So this is the quantum dots, and it is functionalized with amino functionalized material. So this is the amino functionalized graphene quantum dots. When it reacts with the glucose, see these two pieces or the quantum dots, it is joined through this, and thus you can see the glow here, and this is the photoluminescence emission is observed, and this have a dual linear range of 0.1 to 10 millimoles and 50 to 500 millimoles, with an accuracy of 98% and a 97%. So the limit of detection for this PL emission method was 0.01 millimole, and the analysis of commercially available glucose in an instant mixture was done with a 98% accuracy, and it has been published in Spectrochemica of these quantum dots, because of it binds with the glucose. So the size distribution also, you can see here the size distribution increases. See, the size distribution is almost normal here.
Sorry for the network disconnection, sir.
சொல்லுங்க சார். சார், am I audible?
Sir, please rejoin, sir. Again.
Thank you, sir. Thank you, sir.
It is comes out, sir. Just now it comes out, sir. You can please join and submit again.
Okay. Please, sir. Please, sir.
Yes, sir. Connection lost, sir. Please, sir. Please, sir. Please, sir. Okay, sir. So the first person will join shortly. ஓகே சார். ஒன்றும் முடியல சார். அது விஸ்வேஸ்வரன் எல்லாத்தையும் கட் பண்ணி விட்டாப்ல, என் மீட்டிங் கொடுத்து விட்டாப்ல. Sir, few minutes, sir. The resource person will join, sir.
Hello, Dr. Shakti. Am I audible now?
Yes, sir.
Yes, sir. Yes, sir. Thank you, sir. Yes, sir. It is
Okay,
audible,
now
sir.
what about the slides?
The screen is not started, sir. Now it is okay, sir.
Now?
Yes, sir. It is. Yes, sir.
Okay. Sorry, I think it got
Yes,
disconnected.
sir. It is moving, sir, now.
Okay, fine. Now
Yes, sir.
we'll continue with this. The graphene quantum dots, we have used this graphene quantum dots as a sensor for the cobalt and copper metal. As you know that the material, this copper and the cobalt metal, it's also required for our body to function. But at the same time, if it is the concentration is high, then you will have a side effects. So what happens here is the graphene quantum dots graphene oxide is taken and it is at a high temperature. It is broken into small pieces and the quantum dots are obtained. You can see the PL here and glow. Whereas it reacts with the metal like cobalt and copper. The glow ceases, quenches. And this is, of course, you can see here the toxicity of copper or the cobalt to the human body and the plant growth. Now, the material is used as a sensor here. You can see that this is a quantum dots, and when it reacts with the cobalt or copper, it loses its PL. So this is the graph where it shows that this is the PL intensity around for a plain quantum dots, graphene quantum dots, and this intensity for the copper as well as the cobalt. So metal ion which interacts with the quantum dots or through a oxo linkage with the dangling oxygen at the edge of the graphene quantum dots. Now the PL is quenching. Now this quenching of PL is observed with the cobalt and the copper, which interacted with the graphene quantum dots, and it is because of the long range conjugation is obtained there and around the metal ions which relax the excitonic barrier. That is why the PL quenching is observed. So this PL quenching is well utilized in fast the qualitative sensing of metal ions like cobalt and copper present in aqueous media. So we have used same graphene quantum dots to measure the calcium also, and you know that calcium the role of calcium for the human body is it circulates the blood, moves the muscle, relax the hormones, then the neural signal transport, formation of teeth and bone. So this is the advantage, and you can see that there's a disadvantage here, the negative effects of the hard water. You can see in different ways, and this hard water where it finds the form, it's difficult to get the soap lather, and then lime scale is formed on the pipe, and the washing of clothes becomes difficult, and the calcium deficiency that gives wrinkles on body and hair loss, then bacterial problem, then premature aging. So these are the few the disadvantages of having the higher glucose, or I'm sorry, same GQD is absorbance is less compared to the graphene quantum dots. That means that the PL it is reduced here. So the graphene quantum dots is also used, as I said, that's used for the spectrophotometric estimation of a calcium, where you can see that the graphene oxide is taken and it's autoclaved, and then you get a GQD, and this GQD you can see the PL, there's a photoluminescence, and when you put into water, this GQD, when you put into water, it loses its photoluminescence. So you can see here there is no photoluminescence for this, no glow here. And why it is so? Because what happens is the calcium present in water that interacts with the GQD core, and it is observed that an agglomeration takes place, or aggregation of this linkage with the calcium, and is bridging the two graphene quantum dots. So this interaction will lead to the quenching of the PL in the GQD. And why it quenches? Because of the long range conjugation around the calcium ions, which relax the excitonic barrier. So the PL quenching also refers to the turn-off mechanism of sensing. It's a turn-off mechanism. It's called because the PL quenching takes place, and it's employed to determine the concentration of calcium ions. So the method was able to determine the strength of the calcium ions with the accuracy of 96%, and the limit of detection is 5 micromoles. So this is the extension of that same work, and the quenching of PL is because of the relaxation of its excitonic barrier, and this is used in present. In order to compare, we have taken the another study where it shows that what is expected and what is the obtained under the same the graphene quantum dots experiment, and you can see that how sensitive it is. The selectivity for this material, see, in comparison with the other material, it finds only sensitive to the calcium. And the calcium, the quantum dots is used to for sensing. We have used this for sensing the oxalic acid. So oxalic acid, where you know that oxalic acid present in the body, it forms a calcium oxalate, and this calcium oxalate, that is nothing but the kidney stone. So one has to monitor the concentration of oxalic acid in the body, and see, you can see that this is the amino functionalized the graphene quantum dots, and the oxalic acid is approaching this, and it approaches and forms a bond here with this oxygen, and more oxygen, because of the oxalic acid, more oxygen is available here. And here what happens is the reduction of a free acid group takes place, and yeah, see here. This is the graphene quantum dots. Oxalic acid approaches here. It forms the bond with the amino functionalized group, and then the binding of oxalic acid to this amino group on the NH-GQD provided excess oxygen here environment. So this oxygen groups can undergo reduction here, and when it undergoes reduction, the bound oxalic acid provides excess oxygen. This gives excess oxygen, which is rich. It's excess oxygen available on the terminal, and thereby giving the reduction current. And thus, the reduction is possible here. And thus, upon reduction, the available oxygen-rich terminal groups on oxalic acid bound to this the amino functionalized graphene current reduces as no further site is available here. So thus the reduction current is formed, and this can be used as a sensor for the oxalic acid also. And the beauty here is that the response time is less than 2 seconds. And the selectivity, you can see that this is the activity with oxalic acid, and the other the uric acid or a glucose or oxalic acid present. Uric acid and glucose present normally with the blood or the urine. So you can check with that, and it gives a response to the oxalic acid only. So now we have prepared the metal oxides as the glucose sensors, and in this case the titanium oxide is prepared, and it is doped with the vanadium or a nickel or a cobalt, and it's used as a glucose sensors. And so now coming to this another sensor, what we are preparing is a dengue sensor, dengue biosensor, and then the material is used. Of course, it is not published, and we are at the verge of completing the reactions here. So you know that how dangerous dengue is, and we have come up with a sensor for this non-structural protein NS1 as a biosensor, and see how it is working as an electrochemical sensor. Now you know that you have a glassy carbon electrode, and the material is pasted on this and drop casted, and electroactive material it is, and anti-NS1 is present in that. And dengue NS1, when it reacts, it gives a signal, and it goes to the transducer and then amplifier, and the dengue can be detected. So this is the different characterization property of the material that we are going to disclose, or applying for a patent very soon. And this is the overview of the NITK on the both side of the National Highway 66. And Okay, you can see that now almost it's at 12:30 and it's a time for your lunch. And this is one of the snack available in the Mangalore. It's called Goli Bhaje, and it's a highly tasty one. And now you can see that, as I said, the Richard Feynman said in 1959 at Caltech that there is plenty of room at the bottom. So nanotechnology is likely to be particularly important in the development world because it involves little labor, land, and maintenance. It is highly productive and inexpensive. It requires a modest amount of material and energy. So after the conference, the professor is going for it. You can see this slide, and the professor going for a lunch, and the chef says, "Take it, sir, whatever you like, veg, non-veg, Italian, Thai, continental, everything is plenty. Carefully, see carefully. It is the nano food, sir." By the listening to that, the professor really started sweating. So this is the overview of the Mangalore, the National Institute of Technology, Karnataka, Surathkal, and this is the building where the science is placed and the chemistry department is placed. And this is the small achievement from my side. I work on the materials. It's a coordination compounds and nanometal oxides as a NLO material and a catalytic material for organic synthesis. Coming to the nanomaterials, we work on carbon nanomaterials and graphene and metal oxide composite for applications like high yield synthesis, hydrogen storage, solar cells, supercapacitors, catalyst, substrate, and biosensors. And on the other side, we work on the coordination compound as a catalyst, antimicrobial activities, non-linear optical materials, and this is the publications and the student, the PhD guidance. Yes, I need to acknowledge the funding agency, and the funding agency like our institute, NITK, then DRDO, MHRD, then Ministry of Education, then my collaborators from Northumbria University in New South Wales, University of New South Wales from Australia. Is a professor from Korea, where I was there for 2 years, and is from UK. I was there in his lab as a Commonwealth Fellow, and is my colleague in the NITK, and she is Professor Veena Shajwal from University of New South Wales, Australia, and he is my student who was working at the University of New South Wales. And all this happened because of the hard work from my students. These are around 22 students. They work day and night, and because of their hard work, today we are enjoying this research. And this is a photograph where I met the Nobel laureate in 2000, Nobel laureate of 2005, that's Chuan and Robert H. Grubbs. They got a Nobel Prize for metathesis method in organic synthesis. And this is the end of this, probably. I hope you are not using mobile or sleeping. And this is the slide where it shows that this is a very famous ice cream available in Mangalore. It's called Ideal Ice Cream. So in case if you have not visited Mangalore, when you when you come next time to Mangalore, don't forget to eat this ice cream. And this is a world best ice cream available in Mangalore. And they don't have a franchise outside Mangalore also. And thank you for all your patience hearing. And this is a photograph in Manila, somewhere in Manila, taken last year. Okay, thanks a lot, and I take this opportunity to thank the Dr. Shakti Pandey from SRM Trichy, and for all this opportunity, and thank all the audience listeners for your patience listening. And if you have any questions, I'll be very happy to clarify. Thank you.
Thank you, sir.
Hope I have not exceeded time.
No issue, sir. There is a one question in the chat box, sir.
Yeah.
Can the perovskite nanomaterial increases the efficiency at room temperature? If yes, how much?
Could you repeat?
Can the perovskite,
Perovskites, ah?
perovskite, yes, sir, nanomaterial increase efficiency at room temperature? If yes, how much?
Perovskites,
solid.
yeah, I understood. But perovskite, we don't work on perovskites, and it's not fair on my part to comment on that now.
Okay, sir. So there no other questions, sir, in the chat box.
Yes, sir.
Okay,
Thank
okay,
you, sir.
fine. Thank you.
Vishweshwaran, sir.
Yes, sir. Okay, if there is no question, you can further